Yeah, great. All right, well, hello everyone, and welcome to the LINCC Tech Talks. My name is Colin Chandler, and our co-host is Mi Dai. We're both LINCC Frameworks project scientists, and I'm at the DiRAC Institute in the University of Washington, and Mi's at the University of Pittsburgh. The LINCC Tech Talks include presentations and demonstrations that showcase work done by the broader Ruben software and archives community with the goal of further enabling LSST science. And unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSST data. LINCC Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. So today our speaker is Joe Ciuca, Jubilee Joint Fellow at the Australian National University in Canberra. Joe has a background in astrophysics and presently specializes in big data and machine learning. And today we're going to hear from Joe about large language models as well as image data applications. So please do ask questions in Zoom or on the hashtag LINCC Tech Talks channel on Slack. And on Zoom, you can type questions into chat or raise your hand. So as a friendly reminder, these talks are being recorded and they'll be posted on our YouTube channel at a later date. And so with that, Joe, please take it away.
Thank you, everyone, and thank you, Colin and me, for having me here today. I'm very excited to present our work on UniverseTBD. I'll now proceed with sharing my screen. I hope you can all see my screen. I'm just going to hide the video panel. Please stop me at any time if there is any technical issue. I am surrounded by technical experts, so we should be able to go forward with this talk. All right, so today I'll be talking to you about UniverseTBD, which is a very increasingly large collaboration of astronomers, software engineers, research scientists, and AI experts. And we're working together on a mission to democratize science for everyone. So today I'll be speaking on behalf of our team, and I'm very, very excited to show you what we've been working on. So the outline of the talk is as follows. I will start by telling you a bit about what we are, who we are, and why we are. Then I'll provide a brief primer of large language models just to set the scene for what I will present in the second half of the talk, which will revolve around hypothesis generation with AI. And then I'll also spend the last 20 minutes of the talk also discussing our efforts in multi-modal large language models for astronomy, with the AstroLLaVA effort, and also with the AstroPT effort, where we are building large observation models for astronomy. And our hope is to expand beyond astronomy to all fields of study. And finally, in the last part of my talk, I will just provide a keynote of sort of a very simple slide to tell you more about where I think the road will take us in the future. All right, so UniverseTBD is an AI research lab consisting of more than 30 people volunteering their time. We are astronomers, software engineers, computer scientists, and of course, we also have artists spread over 4 continents. And it is indeed a pain to find time to meet, but we make it work. Our mission is very important to us, and we are a mission-driven group. We care very deeply about democratizing science for everyone, drawing from our backgrounds. Some of us come from backgrounds where science wasn't immediately accessible, so it felt very hard to be here. And we now want to use technology to empower people everywhere. Indeed, this is reflected in our vision to empower people to explore, synthesize, and even create knowledge with AI. And we are also, as I said, mission-driven, but to be true to you, we are truly value-driven. We have very strong values in our team, and they really guide us. We have openness, excellence with purpose, fearless experimentation. We like to play with knowledge rather than being terrified of being wrong. We also have junior empowerment. I'm quite junior as well. And most of the junior researchers leading these projects are really at the start of their research careers, and we are very happy to have that. And of course, we rely on our integrity and transparency to keep us going. So a good question to start with is, why start with astronomy? I love astronomy, and that's not just the only reason. The reasons are very, very good. So the first one is that we have simplified privacy management, which means that if we make a bit of a mistake, we probably won't end up in prison. It is, of course, provides a broad appeal. Everyone on this earth can look up and become an astronomer. it is indeed a rich resource for innovation. As you can know from your experience, we are building things that see very, very deep into space and time. And of course, it is, it brings our community together, and we can foster new collaborations, not just across countries, but across cultures and languages. And now I think I'll go into my second part of the talk, which is the primer on large language models. I couldn't start this talk without not mentioning the great work of Dr. Alan Turing. So in 1950, Alan Turing was at the University of Manchester, and he wrote this seminal paper, Computing Machinery and Intelligence. He actually submitted this paper to a journal of psychology and philosophy. And you can see already how far ahead he was thinking. In the very first question, in the very, very first sentence of this paper, he poses these questions: can machines think? He then goes on and says this is an ill-posed question because of the various definitions the word machine or thing can have. It is they are very, very vague. So instead, he proposes a different way to phrase this, to think about this question. And now we have what later on gets called the Turing test or the imitation game in other places. So in the imitation game, what happens is you have three components. You have two humans and then a machine, and there is a judge. The human is the judge, and the judge has to distinguish if text that is being provided to them via the machine and the other human. So let me make this simple. You have three: the human evaluator, and then a human interacting with the machine, and the human evaluator can only see what the machine and the person say via text. And if the human evaluator cannot distinguish which one is the human or which one is the machine, it is said that the machine has passed the Turing test. And just recently I came across a paper that said that GPT-4 has passed the Turing test. I tend to disagree, but we can talk more about this in our questions. So then, in 1966, so 16 years later at MIT, Josef Weizenbaum comes up with this chatbot, ELIZA. And ELIZA is built on a pattern matching framework, and I'll just demo you how it works. So I went and I found the Java interface, and then I started talking to this chatbot, and I told it that I'm feeling quite nervous today, which is pretty much every time I give a talk. And then the chatbot immediately came to me and say, hey, did you say that you're feeling quite nervous today? So it kind of sort of matched what I was saying. And then I asked how can you help me? And then he said, don't you believe that I can help? So it inverted the responsibility on me. By this point, I was becoming even more anxious than when I started, because he was really probing into my ability to know what I was doing. And then by the end of this conversation with the chatbot, I was left more terrified than ever. But then I went to Wikipedia and I wanted to see if other people have had similar experiences with the chatbot. And apparently Weizenbaum's secretary actually told him to leave the room so she could have a real conversation with ELIZA. So other people have had more positive experiences with this chatbot. But then in 2023, we have OpenAI releasing GPT-4, which is a very, very large language model. Think of the order of trillion of parameters. And then I will go back to GPT-4 and I ask it pretty much the same thing. I'm feeling quite nervous. Can you help me? And I'm also an incredibly slow typer, so sorry about that. And of course, the first thing that GPT-4 does is validating my feelings, which is really nice. And then I'm telling it what I'm supposed to do, how to use large language models for science. And then within the next answer, GPT-4 provides actually a few ways to do that. So first of all, you can use large language models for literature review, which is something that we're currently working at UniverseTBD, for hypothesis generation, which is the work of Charlie O'Neill, which I'll present a bit later. And of course, communication and outreach and so on. So when I used this GPT-4 model, I was suddenly feeling more happy about my interaction. So my question then was, what has happened between that moment, between 1966 and 2023? So here we identified, together with our team, we identified a few key sort of milestones. So we have, in 2014, the attention mechanism comes to life via the work of Bakhtanov et al. Then in 2017, we have the transformer architecture, which actually uses this attention mechanism to create an architecture that is able to handle most NLP tasks, a big variety of NLP tasks. Then what happens, in the 2020s, we have there's this boom in GPU resources, and people start training these models for longer. They can also train bigger models because the architectures allow that via, multi GPU or multi-node training. And then finally, we realized that humans are still needed because these base models might not necessarily be aligned with human values or human preferences. So then, in 2021, I think OpenAI comes up with a paper about reinforcement learning with human feedback. And for my talk, I will start now with the attention one. So Bakhtanov et al. With Yoshua Bengio and at the University of Montreal and their collaborators come up with a neural machine translation paper. This paper actually gets miscited or doesn't get cited enough, I think, because most of the time we talk about the transformer and Vasvani et al. 2017, but I think it's a really good paper to always talk about. All right, so what happens in this paper? I wish I had more time to go through the technical details, but instead I will focus more on the intuitive part. If I ask you to look at these cards and actually calculate the sum of all the red cards, what your brain immediately does is pay attention to the red cards and comes up with the sum. In a similar way, an attention layer is a neural network layer that learns to select relevant parts of the input to sort of solve a particular task. So in this case, I asked you what's the sum, and your brain immediately paid attention to the red cards, and then it got the sum. Then, this sort of simple intuitive idea got put into a very nice mathematical framework in 2017 with the Vasvani et al. Paper. This thing got 70,000 citations, which is more than I'll ever get in all of the timelines of my life. So you can see how big the impact this paper has had on our field, on the field of computer science, and not just science, but also astronomy, as we'll see soon. Then in 2018, what happens? We have the first large language model that is trained using the transformer architecture. And then this large language model is used for language understanding rather than language generation. So it's a bit different in its scope than GPT-4, than GPT-like models. And in language understanding, what people really care about is named entity recognition. And then, we also had the nice paper from NASA ADS with the AstroBird to perform named entity recognition in the ADS literature. So you can see how everything fits together very nicely. But I always go to talks and I also teach quite a lot, and I always find it quite difficult to follow when a speaker mentions concepts without really going through the intuition behind them. I am one of these speakers, so I'm trying to change now. So I wanted to make a small mystery for you. So we need to solve this mystery. There's this beautiful LSST camera that we have built, and it's now being very nicely where it's supposed to be in Chile. But let's assume that someone stole the L3 lens at some point. And then we have a set of documents that have inputs, that have clues. And this is sort of the input sequence. Some clues are more important than others in solving this mystery. And then we need to figure out which clues matter most. So this would be the attention weights. And then not only that, you are just one detective, as a detective, you might want to focus on a particular thing like temporal clues or clues about people or clues about the weather even. So that can only take you so far. But if you have a team of detectives where each detective looks at clues in different ways, then you can suddenly start paying attention in more different directions. And what you can do at the end is all of detectives can come together and piece together the full story. So concatenating the attention head outputs. So here, for example, I show you these three interesting matrices: query, key, and value, Q, key, V. Query is pretty much the mystery, who stole the lens. Key is a matrix that actually sort of wants to keep the information of who could be what are the clues, what are the important clues, and V is the matrix that sort of keeps the value of that clue, is how much more important is this clue than the other clue. And I also show this really nice slide that I just found the other day, and I wanted to share it with you. Maybe it's a nice way to see it in a more visual way. So, if, for example, in NLP, our mystery is to predict the next token or the next word in a sequence. So how are you doing? And what we can do is we can sort of transform each of these tokens in a vector. We talk about embedding, token embedding. And then we can, in order to solve this question, what's the next token or what's the missing token if we mask one of them, we can come up with these three matrices to keep this information going. And then we can start, piecing together this matrix multiplication to capture the token-token interaction. We can pass it in softmax to have a nice probability. And then we can multiply this with a value. Each of these matrices are run initially randomly. So they are initialized with random values. And then through training, their values get changed with the goal to predict the correct next token. So so then what you do at the end, you have these various attention heads that sort of get chosen in the beginning, and then at the end, they come together. So then once you do this, what you are able to do is to look at the transformer architecture that was proposed in 2017 and sort of get a bit more understanding into what's happening. For me, I'm a very visual learner, so this helps me a lot more. I'm not great at explaining with words, but I understand things more visually. So for me, having this, encoder part here, what this tells me is that, for example, I can get a very rich and meaningful representation of my sentences, of my text pretty much. So each word can become some really well-informed vector. And how do I get these vectors is by, starting looking at this word in context with other words. And for the decoder part, this is the part where we learn to generate the next word. And similarly, this is also uses this multi-head attention mechanism. So multi-head is pretty much at every step of the architecture. All right, so we started with the attention. Pretty much we want to look at words in context of the other words, and then we find the mathematical framework to keep track of this sort of attention between the various parts of the sentence. Then the transformer comes up with a really nice architecture that allows us also, one, to get this really nice representation of the tokens themselves, but also to predict the next token in a sequence in the decoder part. And then in 2018, we have the BERT, and then BERT is performing very well at named entity recognition. It's not predicting the next word, so it's not for language generation. But because of the advent in compute performance, we now have had, as you have seen online and everywhere, we have this sort of plethora of large language models being released every other second. There are a few key parts here. So in 2021, we have the InstructGPT paper from OpenAI, where these large language models get aligned with what humans want. And the RLHF is still used quite a lot today. There's also this branching between open source and closed source large language models. And for UniverseTBD, we use both. So for the bigger ones, the closed systems are quite performant, and we use that to create things that then can be used to teach a student model that is usually an open source model. All right, so I also want to kind of go a bit deeper into what's been happening in the past 5 years or so when it comes to these increasingly bigger models. So there is this NLP Moore's law for a while that we've been thinking about. So every year it seems that the model size increases by 10 times. Only in 2021 we have this GPT-3 model, which is 170 billion. GPT-4 is already trillion parameter model. And we started with the transformer, which was a 0.05 billion parameter model. So you can see how they're growing. And this growth is, as I said, pretty much driven by the compute and also by the data and by the humans working, of course, on these methods. And then you might ask why, we want to be resource efficient. Why do you want to just keep going bigger and bigger? Why does scale matter? So it seems that large language models require fewer samples to reach the same performance. So in other ways, if you are bigger, you learn faster. But the way that translates in its performance on downstream tasks is that bigger models seem more capable of generalizing into various downstream tasks. So, for example, what this means is that if you take on the x-axis the parameters in the large model in billions, and on the y-axis you have an accuracy on some task, for example, predicting something. Or providing the right answer to a question, or so on, and so on. You can see that the bigger the model is, it can actually the accuracy increases with 0 shot. So with 0 shot, it means you don't give it any example. 1 shot, it means you give it 1 example to achieve that task, and then few shot, you give it a few examples. And the bigger you are, it seems that you can achieve the greater accuracy without relying on like fine-tuning, which you can just few shot these models. So for example, you can see here at the GPT-3 level, 175 billion, it's already achieved with few shot, it's already achieved quite a nice performance accuracy here. And this is better than, for example, here, the 13 billion model. You can see even with few shot how the increase in accuracy changes. So there is a lot of people on Twitter and everywhere. They're sort of taking these results and thinking about, emergence of capabilities in large language models. I personally don't know how I feel about the word emergence, but it is clear that the bigger these models are, the easier it is to sort of make them do a certain thing, and that thing can be of increasing complexity. But as scientists, of course, we want to learn. We want to see how these large language models, big or small, actually perform on really hard tasks. So for example, mathematical reasoning. So when I was a child, I used to, when I was a child, I used to participate in the Olympiad in mathematics back in Romania. That's one thing we do back in Romania. So, and for us, it was always kind of told that it was a very, very hard thing to do, because it was. And then here in this plot on the nice figure I'm showing you, Dr. Igor Perelman, he solved this Poincaré conjecture, which is one of these very, very tough maths problems, 7 hard problems set by the Clay Institute. And he actually declined the Fields Medal and the $1 million prize, which came with his success. So yeah, though I think he's very, very respected by some people like me. And then what happens is that you can pretty much not get to the same level of mathematical reasoning as for those problems, but you can kind of construct benchmarks, drawing from simpler problems, but still quite complex, like the Olympiad in mathematics. So then some very, very fancy people in mathematics came together and they created this very tough benchmark, drawing from problems from the International Maths Olympiad. And then they asked the community of AI researchers to sort of create models that can actually perform very well on this task. And then the winning solution came from this very nice insight called the tree of thoughts. So a tree of thoughts here is when you build these reasoning chains. How you build the individual parts of the reasoning chains is quite complicated and sort of deeply meaningful task. And this paper is very nice. I wish I had more time to go into details. But pretty much the people who won this competition, the Lumina model, actually used this tree of thoughts. They constructed these reasoning chains. And then they actually used also what they call the tools. So then they allow the model to actually use code to sort of propose a few solutions to the problem. And then they use these sort of individual proposals to they sort of use the mechanism to select the best proposal from this from the various set that they came up with. So this sort of model is very small, it's 7 billion model actually, but the fact that they used a very well thought of methodology with tree of thoughts, and also they allowed the large language model to use tools like code, and then had a very nice strategy at the end where they chose the best proposal, actually allowed them to win the competition, securing over 29 out of 50 problems in the International Maths Olympiad. So this is really quite sort of impressive performance. This was actually released 2 weeks ago. So this is sort of state of the art. And I think maybe we can always talk about it afterwards, but my view is that large language models don't necessarily have to be that large to perform incredibly well. Okay, so now we're going into into the reason why we're here. We want to talk about scientific reasoning, and there's a really nice paper in Nature by Kren et al. That proposes 3 different ways that AI can help astronomers and scientists in general, and then astronomers, of course, us. So there are 3 things. One is the computational microscope, which is pretty much, you have very nice simulation that allows you to analyze this data, and then some tools to analyze this very nice data. Then you can use it as a research of inspiration. For example, you can have unsupervised learning where you can identify outliers, for example, in the LSST data. And then the final one, which is pretty much theoretical land, it hasn't really been observed yet, is this agent of understanding approach where the AI autonomously obtains, novel and sort of breakthrough ideas, scientific ideas, but also the AI can explain these concepts, to a human in a way that is indistinguishable from a human expert. So this is very theoretical still, but we wanted to see if we can tackle this problem in a different way and just pose the much simpler problem. Can large language models come up with robust scientific hypotheses? And my collaborators and I, we had this very fun little experiment with GPT-4 a year ago, and then we came up with a very, very simple scale. If you get a score of 1, it's a very bad idea, 3 is all right, and 5 is quite impressive. And then what we did, we pretty much allowed GPT-4 to see between 1 to 1,000 papers. And then we asked it to come up with, maybe I can't remember exactly how many we used, but we asked it to come up with around 20 hypotheses. And then we gave them each a score based on this evaluation criteria. And then we pretty much just got the average, the distribution of those scores. And this is what you see plotted here. And then at the time, we had this sort of tiny insight that if we actually allow another model to critique the first model and then integrate that critique into the hypothesis generation part, then we thought that the hypothesis will become better. And indeed, it seems to be the case, but this is lost as numbers. And of course, what we think we saw in this experiment, we wanted to test much, much better. So similarly, now the feedback it also improves the quality of the critique, not just the hypothesis. But then HypoGen became a part of UniverseTBD, and here I want to credit really the work of Charlie O'Neill. He's a brilliant undergraduate student at ANU, and he's truly leading this effort with the grace of work of Tirthankar and Roberta from Oak Ridge and Meta. And the objective for HypoGen is for us to create a large-scale benchmark data set and a shared task. We want to give this data set to our community for hypothesis generation. And our data set is currently, we're aiming for 100,000 plus hypotheses that were selected from CS conferences and astronomy papers. So the way we do this is we identify a gold standard of human hypotheses, and then we reframe them in a meaningful way. And then we use this approach called the bit flip schema from Stanford, where we pretty much take the paper and sort of represent it as a bit, what is the problem, and the flip, what is the solution. And then we create this very, very large data set. And then, of course, we use GPT-4 for high quality extraction. So yeah, high quality transformation of this bit flip from each of the papers that the humans created. So why the HypoGen benchmark, and why do we need it? I think we need it because as we saw in the experiment that I showed you earlier, we don't really have a scientific hypothesis generation data set that we can test these large language models on. And I think the more we want to probe the capabilities of these large language models, the more we need something like this. And we want to be the first to actually come up with something like this. So in here, I'm just showing you an example of a bit of a flip to kind of get a feeling for our data set. This is a very CS language heavy bit flip schema, but it's pretty much in the first part is saying that prompt tuning is very limited because it cannot handle complex tasks. And in the flip, they come up with another version called adaptive tuning that can actually help with this particular task to sort of train a large language model in a better. So now that we are, before we got the data set, we wanted to actually also do some generation experiments, so optimizing for fidelity, novelty, and creativity. So alongside HypoGen dataset, we also want to create a methodology to generate hypotheses and to see how our method is performing on the data set. And this is the work that Charlie has been doing in the last year. It's not the latest work because we're still to get the latest work, the results from it. But yeah, so with HypoGen, we pretty much create hypotheses. Given a scientific inquiry, we want to come up with a proposal of ideas, and then we put this proposal in a tournament, pick the best one, pick the one that's most creative, and then we pretty much use an adversarial critique. So we have this other large language model that critiques it to get it, make it become more novel, and then we compare it to the existing literature to see how, how high fidelity, if it's sort of similar to our data. I mean, it's not something really out there in the open. So we want to sort of find a balance between fidelity and novelty. And then here, before I show you our results, I want to kind of just guide your attention a bit. So here, this is how we used our evaluation metrics. So you have 3 systems. One of the systems could be a human system A, system B, and system C. And then on the x-axis, you have the loss rate, and then on the y-axis, you have the win rate. And I guess we can just sort of go into one direction. So for example, we can look at system B and see how many times it has won as compared to A or C. And the way we do this is we use a human judge. So we give the human judge, let's say 200 hypotheses generated by system B, system A, like let's say system A and system B generate 200 hypotheses, and the human judge gets them, and then he sees how many times system B wins over system A within those 200 trials. And let's say that, for example, for the orange point there, what it means that is the system B has won over system A because it has a high win rate. And for example, if we look at system C, if it's a low number, then we can say that within 200 trials, system B has actually lost a lot more than system C. So here is our data results. So for example, for HypoGen, for the methodology that I just showed you, we compare HypoGen across with LLaMA, the large language model LLaMA from Meta. Then we compare it with a human, with the real people, so the real hypothesis with the GPT-4 that has been given 3 examples, and the GPT-4 that has been given 1 example. And then we can see is that within all of our trials, HypoGen wins. So the human evaluator is actually unable to, the human evaluator actually tells things that HypoGen is actually a better generator than the either LLaMA, real, GPT-4, and GPT-4 zero shot. And these are just preliminary results. So we have changed a bit the data set, and we are also optimizing a bit the methodology. So right now, what we've done, we fine-tuned LLaMA 380 on an improved data set. So we want to get an even stronger benchmark that we can test against. And then we are currently running inference with these fine-tuned models. So right now, what we're doing is we're generating hypotheses, and we're preparing for the evaluation part, where we have invited a few human experts to actually see how many times the fine-tuned model performs as compared to our HypoGen method. And then, of course, we will submit our findings to AAAI in 2024. And then I want to also say that Charlie has truly been leading this effort. I'm just speaking on his behalf. I wish I could do a better job at it because he's really brilliant. And he's currently on the PhD CS job market in the autumn. So thank you so much also on his behalf for allowing us to showcase his work. All right, so in the last few minutes, I am going terribly over time here. Maybe I just want to kind of quickly go through the flavors of the other projects that UniverseTBD is working on. So far we've talked about hypothesis generation, but as we know, astronomy is a truly, it's a truly multimodal field. We have a lot of images. So surely UniverseTBD wanted to kind of go explore also the capabilities of these sort of multimodal large models. And then here we just sort of show you a clip visual encoder that was proposed in Radford et al. 2021. And the key insight here is that you can take pairs of text and images, and what you can do is you can use encoders to represent the text as numbers, and you can use the encoder to represent the images as numbers, as vectors, of course. And then you can sort of train these clip models to pretty much make sure that in the training set, the image vectors and the text vectors are very, very close together. So they have a very high dot product in that sense. And then on the diagonal, if you have a different pair, so the text of one sample compared to the image of a different sample, you want to make sure that these two are very far away if they're not similar. All right, and then what we do here with this visual encoder here is just this is just a part about the images. We also want to sort of align the visual tokens to the language tokens as well in the language model. So what we do, we use this projection matrix that takes the vision encoders and projects them into the same dimensionality as the language tokens. And then we pass this to a language model. And during training, what we do is we optimize the parameters of the projection matrix and the last two layers of the large language model, I think, just to sort of pretty much what we want to do here in the intuitive way is we want to align the image tokens with the language tokens, and that to make sure that the large language model also knows that. And then simply what happens here, this is a more simple sort of visualization, is that you can pass an image and then you can ask, the user can ask a question, what is unusual about this image? And then because the two modalities have been aligned during training, then the large language model can come and tell you, okay, there is a person doing something they shouldn't be doing on the back of a yellow taxi cab, something like that. So AstroLLaVA is our large language model, is the first specialized astro machine multimodal large model. And this work is led by a brilliant junior researcher, Shara Zaman, being supported by Dr. Mike Smith from ASPIA, who is a world expert in NLP and NLP for astronomy. So what we do here in order to align these two modalities, we use GPT-4 to create astronomy captions and imagery. We use datasets from NASA Astronomy Picture of the Day, ESO and ESA, and we have obtained permission from ESO and ESA, and we are in the process of getting permission from NASA APOD before we release the model. So you have this beautiful image, and you also have this description. So what we do is we create conversation image pairs. So we ask questions about this image, and then we pass that to the AstroLLaVA model during training. And then what we do, we train it with time, so we learn it, we teach it how to align these two modalities. And then we are running some early experiments right now, and we are asking this question, why is this image showing me? And then of course it says something nice about the Milky Way. And why is this important? Why is this model important? Is because we are moving in the sort of in the future where we want to pretty much perform a very quick check of our astronomical images. We can use something like this. For me, mostly is important for an outreach perspective, because you can have a lot of kids everywhere speaking in their own language to these astronomical beautiful images and learn about astronomy. And then finally, in the last very few minutes before I go for questions, the problem is with these multimodal large models, as well with the large language models, it is at some point we will be running out of high quality textual data. In this plot here, you can see what's happening. You can see that the effective number of tokens is going to be saturated, sometimes between 2028, and then these large language models will have, they will pretty much overtrain on the same data set. So that's something that is likely to happen unless human beings start, generating a lot more novel text within the next years. But that is, I think this analysis took that into account, and it's not going to happen. So this is where astronomy comes to rescue. This is where we can sort of think about the brilliant data that we have with the Vera Rubin Observatory and LSST, of course, and will generate approximately 4.4 trillion vision tokens each year. So that is a lot of data coming from our astronomical surveys. And this is a question that two of our wonderful colleagues and also members of UniverseTBD have been posing. Could astro data be suitable as a supplemental text? So Mike and Mark Puerta's company came together with fellow collaborators and came up with this nice idea to train a GPT-like model to see if we can predict the next patch in a galaxy image. So then what they did is they trained a range of model sizes of, I think they used approximately 9 million galaxy cutouts from DESI DR8. And the answer is yes. So what you see in this very nice plot is that the more, like, it's pretty much a scaling law for astronomical vision tokens here, is the larger models actually are more efficient, sample efficient. And you can see that this is nice because that tells us that, you know, astronomical data sort of scales in a similar way to text with large language, with these sort of decoder models, transformer models. And the thing is that we are UniverseTBD, we are open, that's one of our key values, and some of the projects are being run out of our Slack, like HypoGen, because we're trying to make sure that the junior researchers are, you know, being sort of in a quite a cozy environment, whereas the more mature projects like AstroPT are being run on our Discord, which is fully open to everyone, to our community, and Mike and Mark are running this project on our Discord, so feel free to join that if you're interested in this sort of open source, you know, interesting work with LLMs. And the road ahead. So I hope that throughout my talk, I have kind of provided a flavor of what the work at UniverseTBD is. We care a lot about datasets and benchmarks because this actually is a way to democratize science. You know, we inspire the community to come up with their methods to test on our datasets. We also want to do research in large language models and multimodal large models, because my view is that if we can build very special, very good, very efficient models, we can then, you know, port them to universities or institutions that might not have necessary resources, as many resources, and they can sort of it can help them, but also purely for research to want to see how these large language models perform. For example, with HypoGen, we want to create models that reason well. And then finally, we want to bring these insights from the data sets and the research side to create useful tools for the community. And of course, this has to serve our mission to democratize science for everyone. So everything that we work on, we always think about how it serves our mission. And of course, the mission has to empower the people in UniverseTBD, and of course, the people that are outside of our community, our immediate community, to the larger community. So they are brave and they, you know, they start thinking about using AI in ways, or not necessarily AI, just these very nice software tools. And of course, I could only provide you only 3 little projects that we have, but we have a few more. We have AstroTalks, which is, we want to create a very nice website to pretty much query all of the astronomy talks ever using natural language. We have Pathfinder, the brilliant work by Kartik here, AstroTalks, David Hendricks and Olan Kobliszcze. And then we also have a few other projects with a knowledge graph and an AstroLLM, which are the work of Sergio Ramirez from ANU and Mike Wormsley from Ciuca and University of Toronto. Thank you so much. And I think I can stop here. I'm sorry for the 5-minute extra. Thank you.
You're doing great. Thanks. Actually, you're right on time for my book. So yeah, it's awesome. With that, we can open it up for some questions. I see a hand waving from Evan there in the DiRAC space.
Can I ask you, for instance, when you were showing a free shot or hypothesis generation, and then you had an example which was ChatGPT, 0 shot and free shot. Mm-hmm. Like, what does that mean when you're doing hypothesis generation and you're giving shots to the ChatGPT? Are you, like, for each hypothesis trying to give it free examples of similar, or like, what does it mean to give examples when you're trying to do this kind of hypothesis generation?
Yeah, so for example, with GPT-4, it is a bit dangerous because we don't know exactly the training set that it's been trained on. Right. So when we give it the examples, it is likely that those examples were seen during training, but the examples themselves can be something like.
Do you try to match the examples to the hypothesis being generated? Okay,
yes. Yeah. We just give them a few examples. Same to Llama as well. Yeah, just of a bit flip that we know very well. Yeah.
And which is okay.
Yeah. Thank you so much for the question.
Great question. Thanks, Nevin. Andy, go ahead. I see hand waving in the room.
This is really interesting. How much do you think the advances are due to the increase in the training data that people have compared to the development of things like the different architectures, the intention mechanisms? I just wonder whether, are we getting to a point where we have sufficient data that is that is maintained by these companies, that's what is allowing us to really make the advances in these very large parameter models, as opposed to a lot of the algorithm developments have gone on?
Yeah, that's a really good question. It's an open-ended question. I think no one really has the answer. My perspective is that I think the data in this scenario is probably the last frontier. I think right now what we're seeing is we kind of see a saturation point. Most of these like large language models kind of sort of approximate a sort of performance threshold, but we can't really push behind it just because the data can only do so much. So right now what's happening, I think people are creating synthetic data sets, or they're coming up with novel ways to use code and maths and tools to sort of build on top of that data. But in terms of achieving something that people talk about, artificial general intelligence, I think we are nowhere near that. So yeah, I think for that we need probably more than scale, and we probably need more than data. We probably need a different way to think about planning and reasoning and architecture, and the architecture that can support this. So I'm not sure if I'm answering, but yeah, I would say the limits of these large language models are the limits of the data. Yes. Yeah.
I'll use a host prerogative and ask a question. So there's a lot of focus for LSST is going to be on time domain science. I'm loving seeing these tools that are analyzing the single images and giving us a description of what's going on. Do you have any ideas on how that might be? Is it extensible to time domain to be able to analyze sequences of images, etc.? How that might work?
Yeah, I think in this way, I want to credit the brilliant work, I think, of Dr. Francois Lanius. I think he's done a lot of work with sort of aligning the different modalities of images and spectra and time series. So I think what we're gonna do with LSST is we're gonna, and with the other surveys, we're gonna try to find, creative ways to work in a shared representation space for outlier detection. I think we might be able to see certain outliers in different, not just in the time series, not just in the images, but in some sort of shared representation they have. I think that's what I'm mostly excited about AI and the data that we're going to see. Yeah. And yeah, I think the work of polymathic AI, they're building this very large foundation model on all the time series and the images, and also using simulation data. So I think they're really pushing the limit of what's possible.
Great, awesome. Nevin, go ahead. Thank you.
A little bit maybe to continue that, you were showing how using what DES data they were able to like predict the next galaxy cutout trained on the previous ones. Like, can you a little bit elaborate what would be maybe the potential uses that you would get from such a model? I would, for instance, think anomaly detection could be one that you look at either what you predict is what it is. You have some other examples, or what's the end goal of these maybe types of analyses?
So I think I was really encouraged that Mike Smith comes and gives a talk as well, because he's really pushed that. But I think from my more limited understanding of AstroPT is that, you know, I think we want to go from the image space to a very meaningful space.
Right.
In this meaningful space, we learn how different parts of an image, of a galaxy image, talk to other parts of that galaxy image. And if we can create these rich representation spaces, I think that's the goal of this transform models, is to create these very, very strong spaces. Then we can use those spaces for various downstream tasks. One of them being outlier detection. Another one, I don't know, I think that's sort of very, very sort of out there in the wild, but, you know, we can also think about informing the observing strategy. For example, like, are we seeing, I don't know how that would work in theory, but we want to point the telescope some places where, you know, it is likely that we observe something new or something. Some of these thoughts, but I definitely suggest that Mike comes and gives, because that work is really great, and I think the LSST community would also love to hear about the work. Thank you.
Kostya.
Thank you for your talk. It was really nice. I have a question, you know, to ground us a bit about data management, right? So it is fine that, you know, LSST will provide a lot of data, but realistically, how do we, you know, get all this data, preprocess it to put to our machine learning training pipeline? Or how do we get, for example, all archive papers in tech and fine-tune some large language model to be able to, you know, answer scientifically interesting questions, right? About what people already, you know, wrote. Yeah. So how are we going to solve these problems as community?
That's a good question. Yes, a question we think about quite a bit. I think the first thing to do is to bring the people together. I think we have to talk about these needs. Secondly, what we do at UniverseTBD is we talk to the Hugging Face community, and the Hugging Face has created this very nice online platform where we can keep our data sets, and they have a very nice web infrastructure. So most of the data sets that I told you about are currently open source on the Hugging Face platform, and they help us store it, and they help us manage it, and they help us do the versioning of the data set and so on. So Hugging Face is a really nice collaborator in this way. In terms of the very big data sets that are going to come, I think there is soon going to be a paper release that I was involved with. And this paper will release a very large multi-modal astronomical data set. And I think the way we are handling the data aspect with that is like everyone comes together. So the Galaxy Zoo people come together, the DESI people come together, and they pick a subset of the data set and then just put it on Hugging Face as well, and then release it to the whole community for experiments. It's not the whole data, but it is a consistent way to chunk a meaningful part of that data and release it to the whole community for each modality that we have in astronomy. For the future, I think I would probably ask you that question more than I would ask myself, because it's a very hard problem. We are working with some smaller samples. And for the astronomy literature, I think UniverseTBD has the released data set, but I have talked to Dr. Alberto Acomazzi from NASA ADS, and I think they're also in the process of releasing a data set for the community that can be used for, for exploring the literature. So I think by doing the work, more people get more inspired to do this work. So yeah, it's good.
Thank you. Do you think we will be able, so what are the limits of Hugging Face datasets? Do you think we could put, I don't know, 10 terabytes of ZTF alerts to Hugging Face?
I think 10 terabytes is doable. They might need to chunk it in some way, but yeah, but I think moving beyond 100 terabytes, that is sort of too much. Yeah. just the sort of first degree from what I've seen with the data set. So.
Awesome, thank you so much. We only have a minute or two left, but you gave this teaser about ChatGPT 4 and the Turing test. I'm just dying to know what you want to say about it.
Oh, well, I just read the abstract of this paper. I can send it to you afterwards. But in the paper, apparently they asked people to sort of talk to GPT-4, and then they asked people to talk to other humans and sort of say in this interaction, which was the human, which was the model. And I think 54% of the time, the GPT-4 was chosen as the human. So yeah,
okay.
that's
Perfect.
100 files GPT-4 won. So that is quite close to 50. So I don't know. Also, it depends on the humans. I could never pass GPT-4 because it's not funny. So it's one way.
Great answer. Thank you.
Thank you. I can send
Andy, time for just a quick question.
Yeah, can you say a little bit about what are the computational resources that you needed to do the work that you're currently doing?
All right, that's a very good question. So we work with Oak Ridge National Lab, and we are sort of relying a bit on the kindness of Tirthan Kargosal. I think he's given us maybe 4 800s, 800 GPUs. And for us, I think we're not moving more than maybe 4 to 16 800 GPUs. I think that's sort of the number of GPUs and the time, of course, as much as we can. Like we would love to aim for 800 GPU days. I think that would fulfill all of our needs for 2024, 2025. We have a lot of work to do, but I hope that with the new HypoGen release and the AstroLLaVA release, we can apply to get even more time to get resources. But we're always happy for more, just saying. Yeah.
Great, thanks. Great hint there, dropped at the end. Yeah, so we're running out of time, but I want to thank you again, Joe, for this amazing talk. Thanks everyone for attending today and watching online. Our next Tech Talk will be on August 8th at 10 a.m. Pacific, and we're going to be hearing from Raphael Shirley about their LINCC incubator project, the Leclerc's Photo-Z estimator. Please join the LSST LINCC Tech Talk channel and the link, that's LINCC, at lists.lsst.org for more information and future announcements. And again, with Joe's permission, we'll be posting the video on YouTube within the next few days. And thank you again, everyone. Appreciate it very much.
Thank you so much. Thank you.
Thank you.